Welcome back to Differential Calculus. In this video, I want to take a look at the concept of propagation of error. If you've taken a science course, you've likely run across this sort of an idea in the past. If you haven't, this might not be immediately apparent what I'm talking about, but I can get there pretty quickly if I just consider a simple rectangular prism, a box. The measurements of a box are its length, its width, and its height. And you can take a ruler, hold it up to the box in each of those orientations, measure those things, and then multiply them together to get the volume as length times width times height. The question that we have is not how to do that. The question is one step deeper. When you use a ruler or any other measuring tool, there is always a tolerance in the measurement. The measurement that you take is not an exact value. The ruler that you have is only able to measure to a certain level of precision. And so there is error in your measurement. There has to be error in your measurement. It is impossible to make things exact. The question we have is if you calculate the length, the width, and the height, and you know the error that your measuring tool has on each of those calculations, how does that translate into the error on the volume? If you've taken a physics course, especially if you've taken a physics course with me, I can say for certain that I talk about an idea called the significant digits rule, which is a very quick rule of thumb that allows you to estimate what's happening here quickly. I'll show that in this lesson, but that's not the point of this lesson. In this lesson, I want to take things one step deeper. I want to see where that rule comes from and why it is a simplification of what's really happening. Let me get my head out of the way, and I'll show you what's called the differentials method. The idea of differentials comes out of the other notation we have for derivatives, right? dy dx. We write this thing so that it looks like a fraction. What is dx? What is dy? I don't actually have a really good name for that right now. I don't really have a good definition for it. But it's going to allow us to start looking at things a little bit more closely, right? If I zoom in on my ruler and I look at the measurement of L, right? So there's my meter stick. It continues onward in both directions. I have the marking for L here, and there is some amount of space between that marking and the next marking in either direction. I'm going to call that amount of space dl. Or if you would prefer, I've also seen it written as L prime. And that's what we're going to look at. So if I measure my box and I get that the length is 34 centimeters plus or minus 0.05 centimeters. The width is 27 centimeters plus or minus 0.05 centimeters. And the height is 18 centimeters plus or minus 0.05 centimeters. All right. So on our ruler, on our meter stick, or whatever we've used here, the tolerance that we have, we are able to measure these things to the nearest 0.05 of a centimeter. From the very practical standpoint, that means that when I wrote down this measurement of 34 centimeters, it could have been as low as 33.95, and it could have been as high as 34.05. The meter stick, the tool that I used to make that measurement, will not allow me to say any more specifically what the actual value of the measurement is. For our purposes, we are going to write this as L equals 34 and DL equals 0.05. Likewise, W and H are going to be the exact values of 27 and 18. DW and DH are still going to be 0.05. Whenever you use the same measuring tool to measure multiple different things, you generally have the same tolerance on each of those measurements. If you were measuring different things, then that would no longer be the case. Right? For example, if we were measuring the rate of speed, we measured a distance that we rolled a ball down an inclined plane, and we used a stopwatch to measure the time from when we started it rolling to when it reached the end of the plane. The meter stick will have one kind of tolerance, the stopwatch will have a different kind of tolerance. So things can get messier than this, but we'll stick with this for the example today. All right. From here, I am going to use implicit differentiation. dV is differentiating implicitly. The first, dW times WH, and I'm going to write that as WHDL, just putting the differential part at the end. It makes it a little bit neater so that you can remember that DL is a single thing without having to put it in parentheses. Then we will differentiate W, leave the rest the same, LHDW and LWDH. Right. It looks a little bit weird writing it in this form. It also looks a little bit weird because we have three things instead of just two, but that was just the product rule. Then from here, we can plug in all of those numbers. Right? 27 times 18 times 0.05, 34 times 18 times 0.05, and 34 times 27 times 0.05 gives me that dV is 100.8. I can also, I probably should have done this earlier, actually calculate the volume itself. 34 times 27 times 18 comes out at 16,524. All right, so going back to how I set this up in the first place, I can combine these things to say that the volume is 16,524 cubic centimeters plus or minus 100.8 cubic centimeters. For the sake of, well, I think of it as the sake of sanity, our measurement could be off by as much as 100 cubic centimeters. And so does it really make a difference if I write this as 16,524 or 16,525 or anything else? So very often in a situation like this, you will see things rounded to wherever the first digit is in your error term. In this case, it's in the hundreds place. So writing down the solution as 16,500 cubic centimeters plus or minus 100 cubic centimeters really didn't lose any information, but it made it a lot easier to communicate the value. All right. Depending on the particular application you're looking at, that may or may not be useful. I mentioned at the beginning of this video the idea of significant digits, counting up the number of significant digits and using them to report on your solution. And you can still see the height at the top of the screen. Using the significant digits convention, 18 centimeters plus or minus 0.05 centimeters is significant to the 10th of a centimeter, or maybe the 100th of a centimeter, but probably the 10th of a centimeter, which means that the length, the width, and the height all had 3 significant digits. And when we look at how I just rounded the volume, it has 3 significant digits. So the methods work very similarly. This method gets a little bit more precise. This method gives you a little bit more careful control over the error in the situation, and depending on the situation, that might be important. Right? For a general physics class, those of you who are taking physics with me, this is not important. We don't care enough. So something that we can do very quickly is a lot more useful. That's why the significant digits approach exists. But if you do care more, right, if you are trying to put together a research paper for publication, you might care quite a bit. Having something more powerful that you can rely on is also useful. So that's where this comes in. That's why it can be important. But this is calculus class. This is not physics class. All we really care about is this is another application of the idea of implicit differentiation. So I would like you to take a look at the other one that I was talking about at the beginning of the video. An object moving at constant speed has a position x of t given by the speed v times the time t. Oh boy, let's try that again. There we go. My S's and 5's look entirely too similar in my notes. I apologize. But we have this object that is rolling at constant speed. It rolls from the position x equals 0 to the position x equals 10.5 centimeters using the same meter stick that is giving us a tolerance of 0.05 centimeters. The time is 0.625 seconds, and the tolerance on the time measurement is 0.015 seconds. We used a very precise timer in order to calculate that. And so using the same ideas that we talked about with the box, I would like you to figure out, first of all, what is the velocity of this object? And second of all, more importantly, what is the tolerance? What is the possible error on that velocity? All right, take a couple of minutes, see what you can do with that, and I'll see you in the next video.